So good evening, maybe good afternoon and to everybody. So we have the second lecture from Professor Andrey Piatnitski. He will continue on talking on stochastic homogenization. Please, Professor Piatnitski.
Thank you and hello to everybody. Good afternoon, good evening, it depends. And first, we summarize briefly our yesterday achievements. So we are given a standard probability space, which means that it's some set omega, F is a sigma algebra of its subsets, and P is a probability measure, sigma additive positive measure, such that the measure of the set omega is equal to 1. And we assume that this probability space is equipped with a dynamical system, Tx. X is a d-dimensional parameter. X is from Rd. So dynamical system, by definition, should satisfy the following three properties. First, it's a group, and the P at the point x plus y is equal to the composition of Tx and Ty for any vectors x and y from Rd. And for x equal to 0, T0 is just identical map. The second property, Tx preserves the measure P, which means that for any F measurable set A, the measure of the shifted set Txa is the same as the measure of A. It's written here. And the last property, which is very important, which in fact ensures the strong continuity in L2, is the property that if we consider this map as a map of the product space Rd and omega, then this map is measurable with respect to the product sigma algebra. Rd is equipped with the Borel sigma algebra, and in omega we already have the sigma algebra F. So the map T is measurable with respect to the pair. And then we assume that Tx is ergodic, which means that any measurable set which is invariant with respect to Tx for any x from Rd necessarily has measure 0 or 1. Roughly speaking, it means that all the only invariant set are the whole space or empty set. Yesterday there was a question about non-ergodic case. In fact, later on, since there is an interest, later on, I think tomorrow, I will explain, formulate the result and explain the modification which should be done in the non-ergodic case. But for a while, let us dwell on the ergodic case. So then we have a matrix function, matrix random variable omega, which is just measurable matrix function in omega. Let me specify it in a bit more in details. So if we denote the element of A tilde by Aij of omega, then each Aij is a standard random variable on omega. We suppose, and in fact, it's not necessary. The crucial for us is the boundness of the matrix A, infinity estimate, and coerciveness. But for presentation simplicity, we will suppose that the matrix A tilde is symmetric, and almost surely it satisfies the following uniform ellipticity condition. The quadratic form with the vector psi in Rd is bounded from above by lambda modulo psi square and bounded from below by lambda to power minus 1 modulo psi square. For all psi is Rd, and lambda is some given positive constant. So our goal is to consider the following homogenization problem. In a bounded domain Q, we assume that its domain is quite regular, let's say Lipschitz continuous. I don't want to go into the details of non-smooth case, so let's assume that Q is Lipschitz continuous. We consider this Dirichlet boundary value problem. The divergence form operator here. And here we take the realization. You remember, yesterday we discussed that stationarity can be defined in this, can be introduced in this way, that we say that the matrix field is stationary if there is a random matrix A tilde of omega such that this our stationary is our field can be represented as the realization along the trajectories of the group Tx of our random matrix A tilde. So from now on, we always assume that A tilde, our stationary field is generated by a random matrix A tilde and the dynamical system Tx. So we have this divergence form operator with uniformly elliptic matrix A tilde. And I forgot tilde here also. And F is the right-hand side from L2 of Q, and the boundary we assume the homogeneous Dirichlet boundary condition. That's the standard elliptic problem. And under our uniform ellipticity condition, everybody knows that this problem is well posed. It has a unique solution for each epsilon greater than 0. And this solution is element of H1, 0 of Q. So our goal is to study the limit behavior of solutions as epsilon goes to 0. Or this problem is called the homogenization problem for this equation star. Well, now I give the classical definition of homogenization, which is adapted to our particular case. So we say that the problem star admits homogenization. If there exists a positive definite matrix, we call it A hom, such that for any right-hand side F from L2 of Q, the solution U epsilon of problem star converges as epsilon tends to 0 to the solution of the limit problem, which takes the form divergence A hom gradient U is equal to F and Q with the same homogeneous Dirichlet boundary condition. So if for any right-hand side F we have this convergence of solutions in L2, then we say that the problem star admits homogenization, and this limit problem is called effective or homogenized problem. Well, now in order to do some technical steps and to prove the fact that our problem star admits homogenization, we need two subspaces of L2 of omega. I didn't indicate that the spaces are spaces defined on omega. So for any coordinate direction ij, ej, it's in fact J's coordinate vector. So J's coordinate vector indicates the J's coordinate direction. We consider the restriction of our group Tx, our dynamical system, to this particular direction, and T is a one-dimensional parameter now. And then since this group T capital with subindex T ij is strongly continuous, then the Stone theorem applies, and we know that the generators of these groups, we have D of them along each coordinate direction. We know that these generators of these groups are well defined and have the following properties. So the first property, the domain, we call these generators dj. The domain of these generators are dense in L2 of omega. This is just the Stone theorem. Then, if we multiply this operator by the square root of -1, then the operator I dj is self-adjoint in L2 of omega. Typically, it's an unbounded self-adjoint operator in L2 of omega. And in addition, we have the following two properties, in fact, which can be easily checked. That the intersection of all these domains, d1, d2, and so on, dd, the intersection is also dense in L2 of omega. And these generators dk and dj, they commute for all indices j and k. So we have these generators, and then using these generators, we introduce first two linear subsets in L2 of omega to power d. We have the space L2 of omega to power d, the space of vector functions whose elements are L2 of omega. We take first function v from the intersection of the domains, and we form the vector such that the first coordinate of this vector is the result of applying the first generator to v. At the second position, we have the second generator applied to v, and so on. This clearly, this space is a linear subspace in L2 of omega to power d. We take the closure, and the closure is the subspace in L2 of omega to power d, and we call this space L2 pot of omega. Similarly, we consider vectors psi1, zeta1, zeta d from L2 to power d such that psi j belongs to the domain of j's generator, and such that these sums are equal to 0. Again, it's a linear subspace in L2 of omega to power, subset in the space L2 of omega to power d, and we take the closure. In this way, we obtain two subspaces in L2 of omega to power d. First, let us check that these two subspaces are orthogonal. Let's take the functions which generate these spaces. So we take v from the intersection of the domains. We take psi such that the psi j belongs to dj. And then we write down the inner product of the this special gradient formed by the generators of v and zeta. This inner product, since I times dj is self-adjoint operator, this is equal to minus v multiplied by this linear combination, the integral of this over measure dp. And then, since the sum of dj zeta j is equal to 0, we obtain 0 at the end. So indeed, any two elements, one is from the set which form L2 pot and another from the set which form L2 solenoidal, since they are orthogonal, then for the closures we have the same property, but just by continuity. And finally, we have that these two subspaces are orthogonal. But just orthogonality is not sufficient for us. We want more. And so it's written here, what I just said, that L2 pot of omega, L2 sol of omega are orthogonal in L2 of omega to power d. And by the way, by the definition of the generator applied to f at the point tx omega is the same as the usual partial derivative applied to the realization of the function f. This relation holds almost surely. So we have two subspaces. And due to these properties that the generator applied at the point tx omega is the same as taking the partial derivative, we can define these spaces L2 pot and L2 so of omega in a slightly different way in terms of the realizations. So we say that Z belongs to L2 potential of omega if all its realization are vortex free in the usual sense, in the usual distributional sense. So for any smooth function, C0 infinity function, phi, we have this classical relation which is used to define the vortex free functions. Similarly, we say that V belongs to L2 potential if almost sure its realization are solenoidal, again in the usual sense in RD. So we take the realizations, we take the C0 infinity function, we write down this integral, and it should be equal to 0. So that's equivalent way of introducing L2 pot and L2 so. In some applications, the first definition is more comfortable. In other applications, the second definition is more comfortable. Well, and now very important properties of this space, potential and solenoidal, is that they are not only orthogonal, but their direct sum gives us the whole space L2 to power d. In classical analysis, the statement of this type are called Weil decomposition. So we keep this name and we formulate this theorem that L2 of omega to power d is equal to the direct sum of two orthogonal subspaces, L2 pot and L2 so. Well, the proof is, it's not difficult, but it's very long and technical. So I prefer to skip this proof. It can be found in the book by Zhikov, Kozlov, and Oleynik of 1994 in Springer. And you can go directly to the chapter, which is about random operators. And there you will find the proof of this decomposition. It's in fact, the idea is to reduce this to the classical Weil decomposition in RT. So I apologize for this, but I don't have time to present this proof here. It's not difficult, in fact. So important remark that by just definition of L2 potential, the average of any vector from L2 potential is equal to 0. We apply generator, and when we apply the generator, the result has 0 average. Then when we take the closure, this property doesn't change. Well, and as usually in homogenization of elliptic operators, we will need so-called correctors, which will be solution of auxiliary problem. But auxiliary problem here is somehow not the same as in the periodic case. There are some similarity, and later on we will discuss it. In fact, they are similar, but at the first glance, you will not see a direct connection between auxiliary problem in the stochastic case and auxiliary problem in the periodic case. Let me formulate this problem in the stochastic case. We find, given a vector, fixed vector psi from Rd, arbitrary one, we want to find the element of L2 potential such that this expression belongs to L2 solenoidal. So you see what we did. We take our vector from L2 potential. We added a constant vector psi. We applied to this vector the matrix A. Again, I forgot tilde. And we want the result to be in L2 solenoidal. And our goal is to consider in more details this problem and to show that it is well posed and that this problem has a unique solution. So that's the statement of this lemma, this problem, which was just written at the previous page. Maybe I should show it again, this star problem. It has a unique solution. In order to show this, we want to reformulate a little bit this problem in terms of projection of L2 of omega to power d to L2 potential. So we denote this projection by p pod. That's the orthogonal projection of L2 of omega to power d on L2 pod. And then the problem star, you can check it easily, it's an easy exercise, that the problem star can be reformulated as follows. Find theta psi from L2 potential of omega such that the projection of this expression on L2 potential is equal to 0. Here we use the Weil decomposition since the spaces, subspaces L2 pot and L2 sol are orthogonal and their direct sum is coincide with L2 of omega to power d, the problem star is indeed equivalent to this one. So then, since we have the linear combination here of theta psi and psi, we can rewrite this problem in this form with this right-hand side. This is a given right-hand side. And the expression on the left-hand side includes this unknown function theta psi. And now what we can show easily, that the operator which maps a vector function v from L2 potential to this expression, to this vector. This operator in L2 pot of omega is linear, that's trivial. It is bounded, it's also trivial because matrix A is L infinity matrix and the projection is a bounded operator. So multiplication by an L infinity function and applying projection, this composition is a bounded operator. This operator is symmetric, which because A is symmetric matrix, and it is coercive. The only condition which should be checked is this coerciveness. And let us check that indeed this operator is coercive. We take just by definition of coerciveness, we should check that this is bounded from below, but by the square of the norm of V with some positive constant. Well, since V is from L2 potential, this projection can be removed because when we take in the product with an element from L2 potential, we don't need this projection. These two expressions are equal. So this expression is equal to this one. But now the desired positive definiteness just follows from the coerciveness of the matrix A, from the lower bound for matrix A. And we have this lower bound. And then the desired property that the problem is well posed, it follows the standard way by the Lax-Milgram lemma, or even from the Ries theorem in this case, because the operator is symmetric. So we know now that there is a unique vector theta, which solves this problem star. Now, one important remark. You remember that we defined for theta psi for each vector psi from Rd. But if you look at this problem, you will see immediately that the solution theta psi is linear with respect to psi. And since it's linear, it can be represented as theta psi of omega can be represented as some random matrix theta of omega applied to a vector psi, where this matrix is defined in the following way. We consider the basis vector E1, E2, and so on, Ed. We substitute for psi one of this basis vector. We solve this problem for psi equal to one of the basis vector. We denote the solution by theta j. And then we form this matrix theta in such a way that the columns coincide, j's columns coincide with the vector theta j. That's the way to construct the matrix theta capital. And you can easily see that if we apply theta capital to an arbitrary vector psi from Rd, we will obtain the solution theta psi of the problem star. Now, since these theta j are elements L2 potential of omega, then their realizations, theta j of Tx omega, are almost surely vortex free. So the usual rotor is equal to, curl is equal to 0. And then by the de Rham theorem, there is a, for each such theta j, for each realization, there exists a function chi j. It's not indicator function like in the lectures of Francois, it's a corrector. Chi j of x omega, which belongs to h1 log of Rd, and such that the gradient of, it's a scalar function, such that the gradient of this function coincides with theta g of Tx omega. And very important remark, this corrector chi j need not be stationary, need not be statistically homogeneous. Its gradient is statistically homogeneous, but the very typical difficulty which appears in the random case is that the potential of this vector field chi is not statistically homogeneous anymore. We just recover in the whole space Rd this potential, which is uniquely defined up to an additive constant, but we cannot say that it's a realization of some random variable. It's some generic function of two variable x and omega, and it doesn't have the same form of as, for example, theta g. It cannot be represented as the realization of some random variable. That's very important property, and these difficulties, this difficulty was faced by the people who studied this problem in, about 30, 40 years ago, and it was a big challenge how to find the way to go through this difficulty. Well, so now the character is defined. We realize that it need not be stationary, but what we know that its gradient is the stationary field. Now, as usually when we deal with the character, we introduce this expression. We evaluate this character at the point x over epsilon. We multiply it by epsilon. And first important statement, first important property of this character is the property that this expression goes to 0 in L2 log in any bounded domain, and its gradient is bounded uniformly in epsilon bounded in H1 log of Rd. So that's the statement of this theorem, that epsilon chi j of x over epsilon is bounded in H1 log of Rd, and in L2 this expression on for any bounded domain B, any ball, for example, it's not important. We take any ball, and in any ball, this guy goes, the L2 norm of this guy goes to 0 as epsilon goes to 0. Now we are going to prove this very important statement. So first of all, we know that but just by definition of chi, its gradient is equal to theta j evaluated at the point tx over epsilon. Then by the Berghof-Ergodic theorem, now this theta j is statistically homogeneous. So Berghof theorem applies. And by the Berghof-Ergodic theorem, we know that this expression here, the norm of the gradient, of this guy, which is just equal to this expression, and applying the Berghof-Ergodic theorem to this integral, we conclude that this integral for almost all omega, this integral converges as epsilon goes to 0 to the product of the volume of B and L2 norm of theta j in the space L2 of omega. Which means that for sufficiently small epsilon, this guy is uniformly bounded because it converges. So that gives us the first statement, that the gradient of the character is uniformly in epsilon bounded, almost surely in omega. Well, so far we dealt with the gradient, but now we want to prove that character itself tends to 0 in L2. And now we let me recall that the character is defined up to an additive constant vector. So we choose, this vector is in our hands, and we can choose this in such a way that for our chosen set B, the mean value of our character, I can put epsilon here, but it doesn't change anything, so I prefer not to write epsilon here, that the mean value of the character over the set B is equal to 0. Then we have a bounded gradient. We have the function whose average is 0. So we can apply the Poincare inequality. And by the Poincare inequality, the L2 norm of chi, epsilon chi of x over epsilon is bounded. And since the gradient is also bounded, we conclude that the set of the family of characters is bounded in H1 of B, uniformly in epsilon. Now, applying the Berghof-Ergodic theorem once again, this yields that, in fact, weakly, the gradient of chi goes to 0. It's again just Berghof-ergodic theorem. We take the gradient multiplied by arbitrary test function, smooth one. Then we write that the gradient of this guy is equal to theta j evaluated at the point t x over epsilon. And then by the Berghof-ergodic theorem, since theta j is from L2 potential, its mean value is equal to 0. You remember. So as a result, the gradient of the corrector goes to 0 weakly in L2. So what we have? We have these two properties, that the family of correctors is bounded on H1 and the family of gradients tends to 0 weakly in L2. Since it's bounded in H1, we can choose a subsequence which converge strongly in L2 and weakly in H1. And for this limit, the gradient is equal to 0, because we can pass to the limit in this expression, and we obtain that for the limit function, also the gradient is equal to 0. But if the gradient of this function is equal to to 0, then function itself is equal to a constant. But the mean value of chi j and epsilon chi j is equal to 0. So mean value of the limit function is also equal to 0. And the constant whose mean value is equal to 0 is 0. So we conclude that for any subsequence, the corrector epsilon chi j of x over epsilon converges to 0. Then the whole sequence tends to 0 in L2. And that's what we wanted to prove. So this completes the proof of lemma. Well, some comparison with the periodic case. It's very interesting to compare the problem for corrector and the equations which we should solve in the random case with those which we should solve in the periodic case. So if we take this corrector and in X, it's easy to see that in X it solves this problem. Because the gradient of corrector is just theta j, and you remember that this product A times theta j plus aj is an element of L2 solenoidal, which means that for realizations we have this equation. So the corrector satisfies this equation, which is the same as in the periodic case. But the essential difference is now the problem is defined in the whole space Rd. So operator is not of Fredholm type anymore. This problem might have many solutions, and we don't have Fredholm's. Fredholm theorem doesn't apply, so we cannot define corrector through these equations. That's the equation in the whole space, and there might be many solutions, and we don't know. Maybe there are no solutions. A priori, we don't know what to do with this equation. So that's the problem. That's why in this case, the standard equation for corrector doesn't work, and the people who studied this problem long ago, they find the way around, and they first defined the gradient of the corrector, and then the corrector was recovered just by the de Rham theorem. Well, now we proceed with homogenization. We take now a typical omega. What is typical? Typical omega, that's the set of omega, which is a set of full measure. Complement has p measure 0. And we will say that omega is typical if Berghof-ergodic theorem applies to the matrix A tilde itself, to the matrix theta of omega, and to the product matrix A tilde of omega, theta of omega. For each of them, the Bergov theorem applies almost surely. This limit relation, which is stated by the Bergov theorem, applies almost surely. So for these three, if we take the intersection of the sets of omega, where the limit relation holds for A tilde, for theta, and for this product, it will be still the set of the full measure. So we consider only omega from this set of full measure. Well, now let me just recall, this property is important, so I would like to recall that the matrix theta evaluated at the point x over epsilon converges weakly in L2 of Q to 0, because it's from L2 potential, it's columns. And as a result, in this expression, this guy converges weakly to psi, because the first part converges weakly to 0. This property will be used in our further analysis. Well, and now it's very time to introduce the homogenized matrix. We take the product A tilde and this theta plus identical matrix. I bold is used for the identical matrix, unit matrix. And then we define A hom as just the expectation of this product. This element from L2, this matrix is L infinity, so the expectation is well defined and gives us some constant matrix A hom. And then again, by the Bergov theorem, since we consider only typical realizations, typical omega, this expression, which is written here, the realization of A tilde evaluated at x over epsilon, and same with matrix theta, it converges weakly to A hom in L2 of omega to power d square because it's a matrix field. And then this guy, if we apply this matrix to some vector psi, constant vector in Rd, then this converges to A hom psi. This is just a consequence of this first relation. As epsilon goes to 0 and convergence is weak in L2. Well, now there are several ways to pass to the limit, and first I would like to show how to pass to the limit using the famous compensated compactness lemma. It was this method based on compensated compactness lemma was introduced by Francois Murat and Luc Tartar in 1978-1979. The lemma states that if we have two sequences which converge weakly in L2 of omega to power d, to sequence of vector function, Vn converges weakly to V, and Zn converges weakly to Z. And we assume in addition, of course, if we take the inner product of Vn and Zn, then in the product of two weakly convergent subsequent sequence, we cannot pass to the limit. It's well-known property. But if we assume in addition that Vn are vortex-free and the divergence of Zn converge strongly in the space H-1 of Q, then we can pass to the limit in the scalar product of Vn and Zn, and the scalar product of Vn and Zn converge weakly star to the product in the product of V and Z, which means that for any C0 infinity function phi, we have this limit relation, the integral of Vn of x, Zn of x phi, converge to also over Q, V of x, Z of x phi, as n goes to infinity. So I already explained that we take a typical omega, the set of full measure. We consider our problem that we would like to homogenize. It was already written. Let me recall that f is from L2. And it's a classical theory of partial differential equation states that if A tilde satisfies the uniform ellipticity condition, then this problem star is well posed. It has a unique solution. And if we multiply this problem by u epsilon, the solution, we denote the solution by u epsilon. If we multiply this problem by u epsilon, integrate over q, and then integrate by parts, then we obtain the classical, the standard a priori estimates, which are written here. The norm of u epsilon in h1 of q is bounded by a constant multiplies the norm of f, and this constant c doesn't depend on epsilon, only on the ellipticity constant. And the fluxes, which are written here, the L2 norm is also bounded in L2 of omega to power d, but okay, it's clear. So that's just the classical theory of partial differential equations. And now, due to these bounds, for a subsequence we have u epsilon converge strongly in L2 of q to some limit function u0, strongly because we have bound in h1. And u0 is again element of h10 of q, because u epsilon are elements of h10. Gradient of u epsilon converge to the gradient of u0 weakly, and fluxes converge to some L2 function p0 weakly. And since the divergence of this guy is equal to f, the divergence of the limit function p0 is also equal to f. That's a very important property for us. And now we want to apply this compensated compactness lemma. We write the just identity. A is symmetric matrix, so if we write A applied to gradient u epsilon and take the inner product with this vector function, is the same as to apply A tilde first to this matrix, to this vector field, and then take inner product with the gradient of u epsilon. But due to our convergences, which were written here, we have this guy, which is this family of fluxes. This converge for a subsequence to p0. This guy, by the Bergov theorem, we discussed this already. This guy converges just to psi because the first term converges weakly to 0. By the definition of the matrix A hom, this term converges weakly to A hom psi, and the gradient u epsilon converges to the gradient of u0. Okay, I repeat this picture here. And now, since u epsilon is a solution of our original problem, the divergence of this expression is equal to f. So the divergence of this term, it's a constant, so of course it's converging h minus 1. While this element is an element of this function, since theta psi is L2 from L2 potential, this element is vortex free. So we can pass to the limit in the product here. So we know that this product converges to the inner product of p0 and psi, weakly star. Then A tilde of omega, theta psi of omega plus psi, this term, is from L2 solenoidal. You remember our auxiliary problem. This function is from L2 solenoidal. So its divergence of its realization is equal to 0. And W epsilon is, of course, vortex free. So we can pass to the limit also in this product. And passing to the limit, since these two expressions are equal to each other, the limits are also equal. And since psi is an arbitrary vector from Rd, we finally have that P0 of x is equal to a Hom W0 of x. First, we obtain this with vector psi, but then since psi is an arbitrary vector, we can remove this psi and obtain just this vector equality. Well, and it remains to recall that the divergence of P0 is equal to F. And finally, we have the divergence A Hom gradient U0 is equal to F. And as already was mentioned, U0 is an element of H10 of Q. So the boundary condition is homogeneous Dirichlet boundary condition here. So in order to conclude, we need one more property. It's not the end of the story, because this problem will define the limit function U0 unequally. If we prove that the effective matrix A Hom is positive definite. So far we don't know it. So this is the statement of this lemma. A Hom is positive definite. I will not touch the upper bound. A constant matrix is also bound, is also at infinity. So I will concentrate only on the lower bound, which is important for us. And then just by definition, I write the definition of A Hom. Then look, this term is L2 from L2 solenoidal. This term is from L2 potential. So the inner product is 0. So I can add to psi, this theta psi for free. But now I have this quadratic term here. And by the property of matrix A is bounded from below by this expression. And opening the brackets, we obtain immediately this bound. So it's bounded from below by the same constant lambda to power -1 as the original matrix A tilde. Well, and this gives us the desired well-posedness of the limit effective problem. And then the function U0 is uniquely defined, and the whole family U epsilon converges to U0. And this completes the proof of the homogenization theorem. I think we completed it just in time. So I'm done for today.
Okay, thank you, Andrey. I think we have a couple of questions.
Yes.
Shall I read for you?
Yes, please. I don't see the chat, so
No, I can read it for you.
please.
The first question is from Andrey. Is the approach directly applicable to the case of Robin boundary conditions?
Yes, sure. We can consider Neumann or Robin boundary condition. In the case of Neumann boundary condition, we should make probably the spectral shift just to make the problem well posed. Yeah. For any well posed problem, with any boundary condition which make problem well posed, we will have the same result. In fact, the effective operator and the technique doesn't depend on the boundary condition. We can consider again with some spectral shift. If we add some positive potential, we can consider the problem in the whole space in an unbounded domain. The result, the homogenized operator doesn't depend on the boundary condition. So the answer is positive.
Thank you. There's another question from Irina Peterson. Is there any explicit formulas for the homogenized matrix in 1D case? Is it related to the explicit formula in the periodic case?
Yeah, it's a very, very good question. Thank you for this question. It's interesting. In the case, or in the 1D case, it's well known that the effective coefficient can be obtained as the harmonic mean of the original coefficients. And it's a nice exercise to go through this procedure, which we studied today, and to show that indeed in 1D case, the solution obtained in terms of the auxiliary problem will be equal just to the harmonic mean of the coefficients. So like in the periodic case, in the random case, in 1D case, the effective coefficient is just a harmonic mean of the original function.
Good. Yeah. There's one more question right now from Shankar. Suppose we know that character is given by stationary random variable. What are the advantages we get?
Sorry, could you read it?
Yeah, sure. Suppose we knew that character is given by stationary random variable. What are the advantages we get?
Well, I'm not sure if I understood the question.
Okay. Is Shankar can unmute it and answer?
Maybe you just unmute him and.
Otherwise, you can later answer tomorrow. Also, you can read the questions from your thing, and you can answer.
Wait, I will switch off the sharing, and then I will see the.
Yes.
Now I can read the chat.
Yeah. Yeah, there are more questions. Actually.
Yes, just a second.
Yeah, sure.
Suppose we knew the character is given by stationary random variable. What are the advantages we get? I don't know, because typically character is not stationary random variable. Imagine that you have the stationary field, even in one-dimensional case, you have a stationary field with zero mean value. Very good one with finite range of correlation. When you integrate it by the central limit theorem, the result will grow like square root of the distance. It will not be stationary. In a sense, it is never stationary. Otherwise, it would contradict the central limit theorem. But if just by chance it's stationary, well, I don't know. I think this case is of no interest. Well, for numerical computation, it's there is a big activity related to the numerical computation, and one of the methods is as follows. We do so-called periodization. We cut a big piece. Typically we simulate somehow our random media. We cut a big piece of it, and then we extend it periodically and apply periodic homogenization. And there are rigorous results which states that as the size of the period tends to infinity, this periodic effective coefficient converges to the correct effective coefficient for random media. So typically people do periodization. Not only, there are other methods.
Yeah, next one is this very nice presentation. Is this technique also adaptable for non-local operators? Maybe you're one of the favorite topics.
Yes. And recently people started studying random media, non-local operators in random media. So there are two different type of operators which were actively studied. That's Levy type operators with a singular kernel, and convolution type operator with integrable kernel. In both cases, there are results for random homogenization. It was proved in both cases. And there are two ways, either again with corrector. Corrector only method only applies if we deal with integrable kernel. In the case of Levy operator, no way to use correctors. And another way is variational approach when we use the subadditive theorems.
Are you planning to give some discussion tomorrow on non-local?
Well, I will try to. I will not have time to prove something, but at least I will show the results. Yes.
Okay. The final one is a comment from Ainus. Nice presentation. Thank you all.
Thank you.
Okay. Any more questions from the audience? Yeah, it looks like we are probably tired after 4 hours of lectures. Right, Patricia? So the major presentations are over. Okay. And we will have after half an hour presentations from the participants.
Okay. So to everybody, see you in 30 minutes.